A set of samples was sent to the Interface Analysis Centre at Bristol University for examination. The university already had a strong chemical vapour deposition research programme underway.
We were provided with 3 samples by Ernest Nagy. The first was deposited onto steel, the second onto glass, and the third onto a tungsten carbide tool. We examined them using a variety of techniques. We started with scanning electron microscope that you see here, and cathodoluminescence, and we moved on to transmission electron microscopy and electron diffraction. With that, we could also examine electron energy loss spectroscopy. We moved on to Auger spectroscopy and Raman spectroscopy, and then we asked Professor Ernest Nagy at Cambridge University if he could examine the samples using X-ray diffraction. Well, the results obtained using the scanning electron microscope revealed that indeed he had produced films onto the sample surfaces, but these films were very flat. We moved on and looked at the same samples in the transmission electron microscope. This is the samples deposited onto steel and the samples deposited onto glass. And when we moved on to membranes which were observed over holes in the steel, we obtained diffraction patterns like these. Now, the diffraction patterns consist of rings, and one is able to index those rings to see which crystal type the crystal belongs. And in this case, we showed that they belong to the diamond cubic type, which was a good indication of the small crystals we were seeing in the films, in fact, being diamond. Well, we took many electron diffraction micrographs in this way, and here is what's called a dark field electron micrograph, which shows only those crystals which are oriented for diffraction in a particular direction, and that shows the membrane, which is in fact the film, and the small diamond crystals are shining up as little stars inside that membrane. Well, here's a detailed diffraction pattern that we obtained in fact from the film deposited onto the glass, and it shows the diffraction pattern from an individual crystal. And in other areas of the film, instead of obtaining single crystal type diffraction patterns, one obtains these multiple rings. And this told us that the films had undergone some chemical transformation during the deposition process. Moving on to the spectroscopies, this is an electron energy loss spectrum, and one expects to see, if it is a diamond film, a peak in the spectrum rising at just 290 eV, that's the energy loss, and it will have 3 characteristic peaks in that spectrum, and that is a fingerprint of a diamond film. Now, we didn't find that everywhere in the film, but it was conclusive evidence that one does have diamond within the film. The other technique is Auger spectroscopy, and the diamond fingerprint from such a spectrum is as shown here, with these peaks rising in a succession of 3 peaks and then falling to a minimum at about 268 electron volts. Well, what we observed on the very surface of the sample, this is the tungsten carbide, the film on the tungsten carbide, we observed a peak which is not characteristic of diamond, in fact is characteristic of just amorphous carbon. But when we removed that amorphous carbon by iron milling, then we obtained a peak which is much more characteristic of what we would expect from a diamond film. And if we continue to remove that material, then we observe the tungsten carbide substrate on which the film had been grown. And finally here, we're looking at the Raman spectrum. In Raman spectroscopy, we're looking at an absorption line, and for diamond we would expect that absorption line to occur at, in fact, 1331, 1332 centimeters to the -1 wavelength. What we actually observed in the film on the tungsten sample was a peak at 1341, but we think that this shift in the peak position is due to the small particle size and possible strain within the sample itself, in the film itself. The results we obtained from the X-ray diffraction work of Ernest Nagy, here is just one of them, and we see the result of the X-ray diffraction profile obtained from the film deposited onto steel. Here, lines 1 and 2 are lines that we get from the steel itself, but in between these two there's a very small peak, and this is the peak that you would expect to find if there were diamond in the film. In fact, that although the peak appears small here, it is an indication of a rather good film, and it is small because the films are so thin. We conclude from this that there is a variety of evidence obtained from different techniques, all indicating that indeed thin films have been produced which are continuous within themselves, and within the films there is a substantial proportion of diamond crystals. These diamond crystals are not embedded into the surface, but are formed to produce this new film, which is very coherent to the surface indeed.